this one's a bit tricky because it says use with trigonomic substitution, but you'll probably, like hurt your head after a while trying to think about which trigonomic substitution works because of this x squared up here. So actually, we're going to use trigonometric substitution after we rewrite a bit, okay? One trick we have up our sleeve is that we can always rewrite before we try to evaluate an indefinite integral. And after playing around with it for a bit, one trick I thought of was we could use long division to rewrite it equivalently, right? So we're going to take this expression, we're going to rewrite it by seeing what the long division is when you divide x squared by x squared plus 25. And if you do this out, remember the long division technique is you take a number, you're trying to figure out a number that would multiply to be x squared to make it equal this x squared down here. So that's just 1, right? 1 times x squared makes x squared. 1 times 25 makes 25. And then just like long division with non-algebraic numbers, we subtract this top row by this bottom row. And by design, those cancel out. But you got to subtract that 25. And so that's it. This is like your remainder because now there's nothing else we could add up here. So that when we multiply by x squared, it makes 25 without using, like 1 over x squared, without using something that's not it's no way of doing it without using a negative exponent. So this is our remainder. So the way we finish writing this is it's 1 subtracted by the remainder divided by the divisor. Okay, so if that troubled you, I mean, I kind of went over it pretty quickly. You'll probably want to go check out a video on long division of polynomials. So we rewrote the integral. And now you might know what I'm going to do involving trigonometric substitution. Because now we can break this up into two separate integrals. Integral of 1 with respect to x, and then the integral of 25 over x squared plus 25 with respect to x. This one looks like tangent, right? Let me see before I do that, though. I think we got to rewrite it. Because we know the derivative with respect to x of arctangent is 1 over 1 plus x squared. Or if you consider this as a u, maybe in a different problem, just remember the chain rule applies. You'd still have to multiply this by du. But if it's just an x, the derivative of x is 1, right? So just watch out for that. That doesn't affect us in this problem. That's what we're looking at for this type of integral. We just got to rewrite it a bit. We'll factor out the 25 that's in the numerator, and then the denominator needs to be x squared plus 1, or something squared plus 1. So I'm going to factor out a 25 from the denominator. That makes this 1 over 25 x squared plus 1. So just a little bit of algebra there to make it look like our derivative of arctangent. So now, going back to this arctangent derivative, if the derivative with respect to x of arctangent u is 1 over u squared plus 1 times the derivative with respect to u, right? So we need u to be something that's being squared. So my substitution is going to be u equals 1 over 5x. That way, when you square u, 1/5 squared makes 1/25. Okay, and then these are going to cancel out nicely. Let's just evaluate this. This is x, and then we're evaluating the integral from 1, the integral of 1 divided by u squared plus 1 du. Because now it's in terms of u. Actually, du is 1/5, so I made a boo-boo there. Before I continue on, I got to consider what du, the derivative of u with respect to x is. Du is 1/5, so we have to have, we have to balance that out by having a 5, or else it's not the same expression, right? 5 times 1/5 would bring us back to where we landed here. So that 5 out there is important. Okay, and finishing up, now we know this is arctangent, or tan. I hate this notation, but we see it a lot. It looks like it's tangent the negative first. Let's see. Plus that arbitrary constant c. I think we've got everything here. Arctangent u is 1/5 x. And there, now we're done.